Okay, welcome to your first video lecture in section 10.4 on even and odd functions. The reason we want to look at even and odd functions is that the integrals necessary to compute the coefficients of Fourier series can be quite cumbersome, and if we can find any way to make these integrals more simple, it would benefit us to do so. So two types of functions that we'll look at whose integrals are simple are even and odd functions. So recall that a function is even if f of negative x is f of x for all x in its domain, and a function is odd if f of negative x is negative f of x. An even function is a function that is symmetric with respect to the y-axis, like x squared. An odd function is a function that's symmetric with respect to the origin, like x cubed. Like I said earlier, examples of even functions are things like 1, x squared, x to the fourth, and cosine of x. Examples of odd functions are x, x cubed, sine of x, and tangent of x. And much like periodic functions, even and odd functions behave nicely when added, subtracted, multiplied, or divided by each other. For example, the sum, or difference, and product, or quotient, of two even functions is also even. On the other hand, the sum or difference of two odd functions is odd, while the product or quotient of two odd functions is even. The sum or difference of an odd function with an even function is neither even nor odd. However, the product or quotient of two such functions is odd. So one interesting example, the third kind, tangent of x, which is the quotient of sine of x, cosine of x, sine of x being odd, cosine of x being even, this thing is odd, as we stated over there. Okay, but this is important because Fourier series are nothing more than the sum of many even and odd functions. Probably most importantly, even and odd functions can be integrated more easily over intervals of the form negative L to L. If f is even, then the integral from negative L to L of f of x is just twice the integral from 0 to L, right? So if we look at the area of something like this, from negative L to L, we know that we can just find this area and times it by 2. On the other hand, if f is odd, the integral from negative L to L is simply 0, and we can see that because we know that the net area there is just going to be 0 because this guy cancels with this guy here. Okay? And so these properties allow us to see that the Fourier series of an even function will only be cosine functions, since cosine functions are even, and the Fourier series of odd functions will only be composed of sine functions because the sine functions are odd. So again, suppose that f and f prime are piecewise continuous on the interval negative L to L, and f is 2L periodic and even. So we're going to consider the even case here. Since f is even and cosine of n pi x over L is even, the product of these two guys is even. And because sine of n pi x over L is odd, the product of f being even with sine of n pi x over L will be odd. Okay, so as a consequence, the bn's, which are just integrals of these functions, are all going to be 0 because of the oddity of the function. And the an's be the integrals of a bunch of even functions, so they can be just twice the integral from 0 to L of f of x times cosine of n pi x over L dx. And so f being even will just have what's called a Fourier cosine series. So f's Fourier series is just the sum of all the cosine terms, which is quite nice in computation. We don't even have to regard the bn's in this case. On the other hand, if f has all the same properties but is odd, then the cosine terms will be odd because you have an odd function with an even function, but the sine terms will be even because you have odd times odd. And as a consequence, the an's in this case will be the integral of a bunch of odd terms, which will be 0, while the bn's, again, will have the same form as in the previous slide, just with the signs there because of the evenness of the integrand. Okay, so if f is odd, then its Fourier series is just a Fourier sine series. And so from our example from the previous lectures, we had an odd function, right? We had a function where f of negative x was negative f of x for all x. And so the Fourier series is indeed just the Fourier sine series, which we already knew by computing the coefficients by hand. We didn't actually have to do that after the knowledge that we've gained from this lecture. And so we can make our computations much simpler than what we did in the previous lecture by noticing that a function is odd and just regarding only the sine terms. Okay, thank you.